Hello everyone, welcome to my channel. I do educational stuff on this channel, stuff that is hard to find, hard to come by, hard to understand, trying to walk you through it without sacrificing the author's true words. And we are on video number 190 on the reciprocal system of theory from Dewey B. Larson. We've looked at a couple of Larson's books, one of his talks, and a few biographical videos. But we are now looking at the book called Nothing But Motion that came out in 1979. The basic idea of Larson's reciprocal system is that we live in a universe of motion. The universe is made out of motion, not matter and not energy or not anything else, but motion. And motion is the relationship between space and time. Okay, so space and time are set up there to be in a reciprocal relationship. Motion is a fraction with space or time as the numerator and time or space as the denominator. And time or space come in multi-dimensions, 3 or more dimensions. That is what Larson calls coordinate space and coordinate time. XYZ coordinates for space and something analogous to that in time. And then we also have the scalar aspect, which is called clock time and clock space. Clock time, time is always getting later and later and later. It's progressing or it's flowing. And so too, space is also progressing and flowing, which you would visualize by taking a balloon, putting a bunch of dots on it with a magic marker, and then blowing up the balloon. All of the dots are moving away from each other. Then you suck in the balloon, all the dots are moving toward each other. So scalar motion is a motion that has no particular direction, but it does have a magnitude. And in the direction is really either in or out. That's all you have. That's a one-dimensional scalar motion. Now, there are 3 dimensions of scalar motion, ultimately. But we only really can observe one at a time. And then space and time also have their discrete unitness. And so the space and time are not continuous. They come in chunks. They come in quantized chunks. There's a smallest unit of time and a smallest unit of space. And if you have 1 unit of space in 1 unit of time, or per 1 unit of time, the fraction space over time is speed. The car is moving 35 miles per hour, 35 miles of space in 1 hour of time. 1 unit of time in 1 unit of space in 1 unit of time is the speed of light. So the speed of light is basically set up as the 1 in this universe, which has inverse to inverse sectors, where you would use multiplication and division to understand that. Like, so in the conventional system, you start with 0, and then, this is plus and this is minus. But with the reciprocal system, you start with 1, and this is 1 times x, and this is 1 divided by x. So it's a multiplicative and divisive. I don't know that that's the right word, but based on division in the reciprocal system. So in Larson's system, that speed of light is the midpoint of the universe. It's the null point, the 0 point, the natural the natural reference system, the progression of the natural reference system, or even the ether, the origin of the universe. And there's a half of the universe that's moving faster than the speed of light, along with the half of the universe moving slower than the speed of light, which is the half that we're familiar with, which Larson calls the material sector. And that's where Einstein, comes up with his dictum that nothing can move faster than the speed of light. That is true for the material sector. But on the other side of the boundary, faster than the speed of light is the minimum speed of the universe. Larson calls this the cosmic sector. And we don't know basically anything about the cosmic sector. But since we know everything or a lot about the material sector, all we have to do is extrapolate over to the cosmic sector because of the reciprocal relationship between space and time. So what's going on in the material sector, the exact same thing is going on in the cosmic sector, except that you reverse the roles of space and time. In the material sector, you have coordinate space, three-dimensional space, and clock time. The clock is progressing, and it's in these XYZ coordinates. But in the cosmic sector, you have coordinate time, 3 dimensions of time that are progressing or flowing through space, clock space. So you have the opposite relationship: three-dimensional time, three-dimensional space, one-dimensional time. Over here, you've got three-dimensional time and one dimension of space progressing. Okay, so that's basically, the short version. And in this book, Nothing But Motion, we are in chapter 13, which is on fundamental constants. And so what Larson does, this book is primarily on like atomic physics with some organic chemistry also. But what Larson does is he starts with that universe, those initial postulates, and he derives deductively, okay, if these were the basic rules, if the universe is made out of motion, motion is the relationship between space and time, they both have their coordinate and their clock aspects, and they come in discrete units, and the universe is follows ordinary commutative mathematics and Euclidean geometry, which is not totally necessary, but that's part of his postulates. If you have those parameters, then you go through a process of deduction. Okay, if this, then that. Well, then if this, then that. And so that is covered in about 15 videos that I did earlier on his talk called The Outline of the Deductive Development of the Reciprocal System. But so what happens when he does that is he deduces a theoretical universe. And then he basically tries to match it up with the scientist's universe from observation and measurement. And that's what he's doing here in this chapter. We just got done with him deriving mathematically and theoretically all these different numbers, which are what he calls secondary mass. And he uses these secondary mass numbers in order to calculate the mass of all these different subatomic particles. So here he says, we may now apply the calculated values of the several mass components as given in the foregoing paragraphs to a determination of the masses of the subatomic particles described in chapter 11. For convenience, these values will be recapitulated as follows. Okay, so we have primary mass. Primary mass is 1.00000. And then we have magnetic mass, which is 0.00639,205. That he got from the fraction 9 over 1,408, which is which is the uh, the reciprocal of 156.44. And that comes from, he explained it earlier, it comes from 128, which is the number of the number of directions. But then because you have within an atom, you have two photons so that it adds an additional 2/9 to that number. So you have 128 times 11 over 9. You take the reciprocal of that, you get 0.00639205. Then for gravitational mass, you add those two numbers together, the 1 and the 0.00639205. So you get 1.00639205. That is the gravitational mass. But now you can also throw in the electric mass in 3 dimensions, that number, and then he uses 128 times 1/9 in this situation because they're in different regions. So you have to multiply them rather than adding them. And you get 0.000868806. And if that is in 2 dimensions only, then it is 0.000578770. And then you have the mass of the normal charge, and that is done by multiplying consecutive interregional ratios, that number 156.44. That is 0.00004494, and the negative electron charge, which is 2/3 of that, but negative, which is negative 0.00002996. So he's getting down to pretty exact numbers, and eventually we're going to get around to comparing those numbers to the found values that the legacy scientists have come up with through their observations. Now, what this is really, this is a natural scale. So it has to be converted to the conventional scale, the scientist scale. So sometimes he has to use a conversion factor to convert from natural units coming from the reciprocal system with the conventional units that the scientists have used, which are often arbitrary, but not always. Okay, these are the masses of the various components on the natural scale. The measured values are reported in terms of a scale based on an based on an arbitrary assumed mass for some atom or isotope that is taken as a standard. Okay, that's generally how the legacy scientists do it. They say, okay, hydrogen is number 1, for example, so we will base our scale on that, for example. In this case, they use oxygen, the 16, oxygen 16, isotope 16. Okay, for a number of years, there were 2 such scales in common use. Okay, let me go back here. The measured values are reported in terms of a scale based on an arbitrary assumed mass for some atom or isotope that is taken as a standard. For a number of years, there were 2 such scales in common use. The chemical scale, based on the atomic weight of oxygen as 16, and the physical scale, which is assigned the 16 value to the oxygen 16 isotope. More recently, a scale based on an atomic weight of 12 for the carbon 12 isotope has found favor, and most of the values given in the current literature are expressed in terms of the C12 scale. In the light of the finding of this work, the shift away from the O16 scale is unfortunate, as the theoretical development indicates that the O16 isotope has a mass C exactly 16 on the natural scale, and the physical scale is therefore coincident with the natural scale. It will, of course, be necessary to use the natural scale for our purposes. The observed values quote for comparison with the theoretical masses will therefore be stated in terms of the equivalent oxygen 16 physical scale. Here again, we face the same issue that was encountered early in this chapter in connection with the selection of an empirical value C, Avogadro's number, as a basis for calculating the unit of mass. The question as to whether we should regard the most recent determination as the most accurate. It would appear that the arguments that led to the acceptance of the 1957 value of Avogadro's number are also applicable to the particle masses, particularly since the agreement between the calculated and observed masses of the electron and proton is quite satisfactory on this basis. The empirical values cited in the paragraphs that follow have therefore been taken from the 1957 compilation by Cohen, Crow, and Dumont. Since mass is three-dimensional, an independent one-dimensional or two-dimensional rotation has no mass. Nevertheless, when such a rotation becomes a component of a three-dimensional rotation, it contributes to the mass equivalent of that rotation. This amount that a rotation which is massless when independent will add to the mass of a particle or atom when it joins that combination of motions constitutes what we call potential mass. In the case of the particles with no effective two-dimensional rotational displacement, the electron and the positron, the appropriate unit of electric mass is 0.0005787 is the entire mass of the particle, and even that mass is only potential rather than actual, as long as the particle is in the basic uncharged condition. When a charge is added, the effect of the charge is distributed over all three dimensions by the chance process that governs the directions of motion of the charge in the time region. And again, that is the chance process because it's a scalar motion. Scalar motion doesn't have a direction. So the directions are determined by chance and in the time region. Thus, the charged particle has effective motion in all three dimensions, irrespective of the number of dimensions of rotation. This not only makes the mass of the charge itself an effective quantity, but as indicated in chapter 11, it also raises the potential mass of the rotation of the particles to the effective status. The net effective mass of the electron or the positron is then the rotational value 0.0005787 less the mass of the charge 0.00002996 or 0.0005487. The observed value is 0.0005487. Okay, so he's got it correct exactly out to the first 7 decimal places. The massless neutron, the M 1/2-1/2-0 combination, again, those are the 3 rotations that go to form the atoms and subatomic particles. The first number is the primary magnetic two-dimensional rotation. The second number is the secondary two-dimensional rotation. And the third number is the one-dimensional electric rotation. An atom is a combination of motions, in general, a combination of rotations. So the massless neutron has that notation m, m meaning it's in the material sector, and then 1/2 dash 1/2 dash 0. Has no effective rotation in the third dimension, but no rotation from the natural standpoint is rotation at unit speed from the standpoint of a fixed reference system. This rotational combination, therefore, has an initial unit of electric rotation with a potential mass of 0.000578770, in addition to the mass of the two-dimensional basic rotation, which is 1.0063205, making the total potential mass of this particle 1.0069775. In this connection, it should be noted that the electron and positron also have rotation at unit speed. No rotation in terms of the natural system in the two inactive dimensions, but those rotations involve no mass as they are independent and are not rotating anything. The initial unit of rotation in the third dimension of the massless neutron, on the other hand, is a reverse rotation of the two-dimensional structure, and it therefore adds an electric mass unit. Okay, I think we're going to stop there. He's going to get into the neutrino next, calculating the mass for the neutrino. But this is all just pointing out how Larson derives a theoretical universe, his universe, purely from his theory and the deductions thereof. And then he compares it with the actual scientific, numbers that they got from their observations and measurements. Okay, thanks for tuning in. We'll see you tomorrow. Have a great day.